So the title of this webinar is More Options for Solving Jobs with Many Tasks. It's going to be primarily demo-based. It turns out there's excellent material on the Compute Canada website and the wiki pages, in particular for this, the new option being META, which is kind of the goal to reach the meta stage in dealing with lots of jobs, if this is your situation. But to get there, because you may already be familiar with GLOST and job arrays, maybe that's what you're using. I'm going to start with those and kind of as a refresher, and it's a bit of a potentially easier to grasp in what we're doing, and it gets us ready to work on the meta stuff. So I'm just going to get to the Compute Canada GLOST page, which you have, and just gloss over it basically, so we can remind ourselves what GLOST information we have available to us and what it can be used for. So the primary thing is for submitting serial jobs, similar run times. You've got a large number of short serial jobs. And if you want to do something with parameters, to do parameter sweeps, we're going to look at an example for that. So with GLOST, it's a little bit, even though we're computing serial jobs, GLOST itself is based on Parallel MPI under the hood. So even though we're talking about computing serial jobs, we're also talking about submitting a parallel job. So we need to sort of get that straight in our heads first, what we're doing. And that's actually one of the first issues with GLOST, is that while it does have some advantages, and it was quite an improvement a few years ago in how we do things, it's a little bit problematic when you need to submit a lot of parallel jobs, a lot of serial jobs, because it forces you to submit a rather large parallel job. And if you've tried to submit a large parallel job, you know it will sit there potentially in the queue for a while before it starts. So that's one of the issues with GLOST, but nonetheless, narrow this down. We can go over how we use GLOST, because it still may be a tool that you prefer to use if you're not doing, if you do a moderate number of jobs, say less than I don't know, 64. Once that's sort of your goal to compute for throughput, then GLOST would start up pretty quickly for you. And it's probably on the surface, to get access to using it, it is maybe, it's fairly easy to use for what you get out of it. So what we've got with GLOST, what we have to do is compute, with all our methods, is compute a good runtime estimate for it. So you've got many serial jobs that you want to compute. You're going to compute them not in serial, but in groups of simultaneous jobs. And that's going to be the size of the parallel job that we're going to submit. And to get the total time, we're just going to take the total time of all the jobs and divide it by the number of simultaneous jobs that you'll be running at the same time. So this is our formula here in the wiki page. And like many of the other Compute Canada wiki pages, we've got SLURM scripts provided to us, which is great. So with the SLURM script, you have to do something else, and you put the commands that you're going to run into the second tab here. So this is what it's showing, and that's taken by the script. And the script will say, okay, I'm going to process each command in this task list and in such a way that it runs as a parallel job. But you don't have to worry about all that because it's handled by GLOST itself. We do need to understand how the SBatch parameters are working. And so that goes on through here. Example further down, which is going to be the starting point. So this script here, it shows us that we're going to run two jobs at once, and it's going to process this table of commands, and you can decide how many of these you want to do simultaneously. We'll call them cases, because when we get talking about meta, each line is a case. So to process this line, you read it left to right. So it's going to set a value for the argument, and then the command itself is going to be done. It's going to sleep. And then when it's done sleeping, it's going to write some output into a log file based on the argument as the parameter. And so we can check. So we're going to do an example just to check to see how that works. In addition, we are also going to do this example, so we'll take a look at it here. It's a very similar, the GLOST submit script. The lower part of this script is identical for all your jobs you're going to submit. It's hard-coded there with the modules that you need to load. That's not going to change. And the name of this list, GLOST tasks, which is being provided in this tab, is the same all the time. I mean, you could change it if you want, but we're not going to. We're going to go with list GLOST tasks text. And these commands will be, for this example, each one of these commands will be processed, computed, and it's slightly different here. It's a little bit longer. There, now it fits on one line. It'll create, well, let's just look from the left to right, because we have to read our GLOST task script, get comfortable with doing that. So let's look at the first line. It sets an argument value. It's going to create a directory with that argument value. It's going to go into that directory. It's going to run the sleep command. Now, sleep could be any command that you're trying to run that might generate output into that directory. But in this example, it's just sleep. That's the thing about sleep. Sleep is analogous to, think of sleep as the program that you're running, that you want to run, and you'd substitute it in here. Anyway, since sleep doesn't output anything, we go one step further and it writes some output. And because we're in the run directory, it's now going to put this log file, which is the same as the previous example, into the subdirectory. All right, so that's enough now to take a look at some examples for the demo. I have to keep me moving. So I've got a bunch of examples here, and the first thing I want to do is demonstrate what the command line version of GLOST. So you can run the command outside of the scheduler if you want. So I've got a directory here and a run script. So what I'm going to do is the command that's in the task list, that can be run on your command line. So I'm just showing you the two examples in the wiki page are here. So the one in blue is the first tab above, and then the one we're just looking at is here. So you don't have to go through. Obviously, you can run these commands in the command line because it's just like running your program. That's the point of, it's just like, this is like one of your serial jobs, right? It's just kind of a long protracted thing there. So, so if I just run it, so it's running this command and it's sleeping for 10 seconds. First thing it did was erase the previous log file from any run. So anything that's in the directory now is generated by this. So before we get something like a massive number of cases into the task list and everything, it's good to know, just does it run on the command line properly before you commit yourself to trying to troubleshoot something that doesn't work when actually it was way back in the beginning before you even, before you even got going on it. So there it is. So the first command wrote the text file, and it included the argument value, which was 1, and then the host name. And then the other one, it wrote the same thing into a directory, except the one it ran was narg equals 2. So we're going to expect, be surprised if there's a 2 in here. Excellent. So that's worked. So pretty confident now we can create our task list. And so next step to getting to using GLOST is I can run these not in the GLOST framework, but directly with MPI. So let's take a look at how we would do that. And this is alluded to in the wiki page. So you can just run the MPI run command to launch it. So we're not going to launch it through the scheduler. I'm just going to launch it here on the command line with MPI run. So this is going to let me run multiple commands at once. And it's going to, in fact, so this, I'll just start it running. So it's working through the task list, which was the example. This one, basically this one on the wiki page. It's running 3 at a time. So I've got number of processors is 4. So it's running 3 ranks. The first one is actually the GLOST process. So it ran 3, 3, and 3, each one taken 30 seconds or so. This whole thing took 40 seconds, and then it's catted out what the contents of the files are. So we can do it on the command line. Again, this you could be testing if it works before you actually submit to the scheduler. Of course, you don't want to do that on the, you normally, if you're actually running something, you do that through on a compute node through an SLX session, for sure. All right, so let's, oops. So there's the task list that we're going to run, and here's our script. This is our SLURM script, which is the first tab over here, script. And run GLOST, notice it's run GLOST test. Here, list GLOST. So I'm not changing anything so that you can go back and do this yourself. So cat run, so we need to submit it to scheduler. So I've got a submit script. So my submit script just runs sbatch on the SLURM script, submits it to the scheduler, and it's going to do exactly as the last interactive demo that I just did. It's going to run 3 of them simultaneously 3 times, and it'll be done. So kind of hoping it takes about closer to 30 seconds than 40 seconds. That could have been, there's some, I don't know, some load on the login node or something. So I've submitted the job. It's got 4 CPUs. So GLOST has had to grab 4 CPUs all at once to run this. And then it says, okay, I can go. So we had to wait. Notice there was a bit of a wait there. That's not the best. So 39 seconds, so it ran them. So good, everything finished. These jobs are all sleeping for 10 seconds. Everything finishes all at once, those 3. So that's a pretty good setup for GLOST because it's efficient. Now let's look at a case where one of the tasks that you're doing is, let's going to run longer than the rest. So the first one it encounters in the task list, it wants to go for 60 seconds. That's how long it's going to sleep. Well, the others do 10, 10, 10, 10, 10. So what's going to happen here? Well, one of them is going to obviously run for a lot longer than the others. And so let's just submit the job. We can see that happen. And we're going to notice because when I just ran it the last time, it finished in 39 seconds. So this time it's not going to be, it's going to be at least 60 seconds. That's what we would expect because of this one process in your task list. That's all it takes. And everything else is going to finish up and it's going to be sitting there wasting the resources of everything while this one task is reaching its end time. When I submit these jobs, I've asked for 5 minutes, so I have plenty of time. So these jobs can all finish. That 60-second job, they'll have 4 minutes to spare. So it's crunching through the task list, the ones that are 10 seconds, it's knocking those off, but it's still, that one process is stuck on the 60 seconds. Waiting for one more. We're waiting for the last one. So there it is. So there's your list. All those seconds. There was one we had to sit there and wait for, and lo and behold, thing took 63 seconds. So all those, the other two cores that we had, they had to wait for like 20 seconds each. 30 seconds each. So that was some wasted cycles there. So that's why GLOST, you should have your jobs should try to finish up at the same time. So that's my point with that. Now, this has just been running on one node, and you have that kind of control with GLOST. And so let's go and let's just submit them to all the nodes. And so again, everything's running for 10 seconds. So are we going to expect any difference in the time compared to the first case, which took around 40 or 39 seconds? Well, here we are, it's computing 3, it's going to do 3 at once again. But it's doing it over 4 nodes. So again, one of the nodes, first the master process, it's not doing any computing. It's the other 3 that are doing everything through the task list. So it kind of looks the same. The only thing difference here, this isn't showing it yet, but you're going to see it here at the bottom there, the output. Now it's grouped the output, and you can see that the log files containing the host names that they ran on, they're sort of grouped, sorted together there. 3 ran on one node, 3 ran on the other, 3 ran on the other. So took 32 seconds. Interesting, that was took less than running it on one node, but basically it took the same time. Maybe I should have been showing more to the, maybe now is a good time. I didn't do it for the first 3, sorry about that. But the actual SLURM script, each one of these cases, I've altered the parameters in the batch prologue here. So these define how many nodes. So in the previous 3 cases, it was running on one node, and this GLOST let me set it to 4 nodes and use 4. these are just commented out. Because the first time I ran it on one node, this is what it was before. One node, 4 tasks. But now I'm doing 4 nodes, 1 task per node. So 3 are doing the computing and 1's the master. So that's sort of, you're not going to do, neither one of those situations are ideal because you're sort of forcing yourself into using certain nodes in a certain way. And instead, it's better to think about it in just submitting the task to any node. So that's what this next example will do. So this one, I will show it. So looking in the batch parameters, now I've commented out, again, this telling it to use one node, that's off. We're not going to do that anymore. And we're not going to tell it how many tasks. Instead, we're just going to, task per node. So we're just going to say run 4 tasks. So that could be on any nodes. So this is your best bet when using GLOST because it will find the first freely available nodes and run the processes on those. So it may end up running on one node if it can get 4. Probably it will just get one node with 4 on it. But if this is running a lot of tasks at once, it would, you'd be limited with one node to 32 cores or 44 on Graham. So if you wanted to run 128 at the same time, then it might run 128 nodes potentially if it can, or it might run on 4 nodes if it's perfectly distributed. Probably won't be. It's going to be something in between. And so anyway, so what's going to happen here is what's the point of doing it like this? The point is that it should run faster because they're all going to start. Well, it's not going to run faster. It's just going to run on the different nodes that it selects. Sorry, that example is coming up. So it's not going to run faster because we're only running 4 tasks, which is exactly what we did before, except we were on one node or we were on 4 nodes. This case is just sort of randomly, it's picking its own nodes. And if you look here, you can see this is in your output, you can tell it to display what the task per node selection is. So it's just saying it's got 4 nodes, which it does. And there they are, they get the output went to those nodes. All right, to make it a little bit more interesting. So this is instead of just 9 commands, that's what we've been looking at. So I've got 90 commands in this list file. That's our command list that it wants to compute. And in the SLURM script, I'm going to tell it to run 30 tasks. So find 30 nodes, and it's not going to start till it gets 30, but that's not too bad of a number because it can put them on any nodes, any compute nodes that it wants. So are we going to be waiting a long time for this compared to the other cases? A lot longer? No, it's correct. I got it right. So this should come out. If it's running 30 simultaneously, 10 seconds for each group of 30, it should come out to around 30 seconds. There's going to be a bit of overhead, but let's see how well it handles that. Okay, so it's done and it's tried to print. There's just too many notes for this to make sense, but you can see that it ran on a bunch of nodes. What's up here is, right, so it ran in 43 seconds. So we're able to run a lot of jobs. They're starting to get more interesting. First it was 9 jobs, now it's 90. We're still keeping the time the same, but the thing is I had to use more, a larger parallel job. I had to start a larger parallel job to get this to run. So still not a problem at 30, but I won't go any further with that. There's a limit of 1,000 on gram, so but that could be, you might not want to do that with this. I'm not sure how far you'd want to go with GLOST if you don't have a rack or something like that. Maybe 128 or 256 or something. Okay, so right, so I got another example here. And again, it's just back to our 9 list, and then this one is interesting because it's a larger memory problem. So each one of these uses larger memory. So I've just put it to 32 and told it to use 4 tasks. So it's not really anything special, but it'll have to work a bit harder to find notes with those sorry. Bad. So if that was like, say, 120 gigs, it would definitely find 4 nodes. And that one node's going to be wasted by the way that it's got on the master, which is not good, but it's a massive job, then it doesn't matter that much if you're getting it done quickly. So GLOST is now let me, potentially work with large memory. Lots of jobs with large memory. Got control over that. All right, so there was, sorry, it's not that interesting yet. It's gonna get better. Oh. All right, so the second example in the wiki page was something that created a directory, then it ran the program, sleep inside the directory, and wrote out our file again. So I just wanted to show that one. And looks like we're going to be on one node, 4 tasks on that node, no big deal. So again, this is going to take like 30 seconds to get through them because there's 9. So just be patient for a minute here. It's my priority is starting to drop. It shouldn't. I'm using a special account that staff have for submitting jobs, so it makes this all possible. All right, so there's really nothing special about this other than the command that it's running is creating directories. And it's from the wiki page, so it's probably something you want to do. Putting your work for these jobs in different directories, so being aware that that's possible is more or less more important than actually how to do it, because it is so easy. And I kind of hope you're seeing this is all getting pretty easy. It's all the same, just slight changes to things here and there, knowing what you want to do. So, all right, so it is possible to run a threaded job. I've got a program here to compute pi, provided by one of my colleagues, and if you tell it to use 2 threads, it's gonna use 2. And so the thing is, we're submitting a parallel job going through our list of, let's look at the list. And this time the list involves running, instead of sleep, it's getting closer to something you might actually do, is going to run this binary, threaded binary, and write some output that it generates into that log file. So get a little more useful. And then we need to get the settings right in GLOSS. So that's going to occur at the top of the file, because I think really what I should say is at some point in all these run scripts is don't change anything below a certain line, which is about here, load GLOSS module. That's basically anything below there, we're never changing. That's sort of the pattern here. And we're just fiddling around with the stuff up here. So we're going to launch parallel job again, 4 tasks, and then we're going to say each one of those tasks is going to get 2 CPUs. We're on 1 node, so we're going to have 3 processes running with 2 threads, hopefully getting 200% CPU. To tell the program to do this, we sort of set the threads from what the scheduler sets, SLURM CPUs per task, which is getting it from up here. So all pretty easy. And I'm going to print out that additionally, that little extra piece of information, just because it's good to know that for the record what was used. Oh, I also echo this thread, so you would know also that that's what was used. But so let's run it, and then I'm going to try to get on the node, the compute node where it gets. That's why I'm using nodes equals 1, so that we can sort of watch it a bit. So I'm going to clear that off and so here we are on grade 284. And let's just get on that node and see what it's doing. Oh yeah. So we're running threaded job in GLOST. It is possible. If you know what you're doing when you're setting the SBatch parameters. We're going to see something like this again in META too. And it did compute pi. Nice. So that's GLOSS doing a threaded. So we had, all right, so still got 2 more examples in this GLOSS. So maybe I got too many going here, but it's all right. Get your money's worth. Parameter search. What are we trying to do? We're trying to vary some parameters over some, in this case, linear scale. I just called them, they're just integers, 1 to 3 in 2 different dimensions. And that could be plugged into, say, if you had some A dot out, they could be arguments there that's computing some result. So you're going to sweep in the 2 different directions. And well, let's just remind me what I put. So 1 node again, 4, and we've got 9 here again, 9 cases to get through. So we're going to be doing 3 at once again. This is all kind of similar. So this was I think the promised parameter search point in the, if that's why you came out. These are the 2 examples that are touching on that. So there they go, and you can see it right there. They set these, there's more than one n argument here. There's two, arg x and y. I don't know, it's not really a trick, but so to generate that, I didn't create that list myself. So it ran in 32 seconds. This list, I did not do that myself, but I generated it. I've like with a just with the basic for loop, wrote it out to that file. So let's do one more and let's go for the 3D example. So we've got now another parameter. So you could have as many parameters as you want here. It's all just a command on this line. It's basically what you've done. And it's setting those. And it's going to output that to the log file, what each case was. It's going to give the name, the dimensions, the combination of dimensions. It's going to be output into the log file, which also has those. So there's, you can't miss it. That's the one that you've done. And yeah, same as before. So what's, how many lines do we have this? Yeah, 27. So that's because the extra dimension. And if we're doing 4 at once, 3 at once, so it's going to take a bit longer. I should have doubled that. I should have increased it. Yeah, maybe I'll just unit. So I'm going to run 9 at once. There you go. So there's the first 9, next 9, more. And it's outputting the files. So it's written all the files. There's the, and these could be, anything. So that's it. All right, so it's done. So it worked. Right, so we're done with the GLOST stuff. Now as a refresher on the job array, let's go a lot faster and we can dive into meta. So the wiki page for job arrays, you search on job arrays, you're going to find it. Just same way with GLOST, you type in GLOST up here top right. That's how you find everything on docs. So the job arrays are a different way of letting us run jobs simultaneously. for many tasks, but there's a lot more overhead here than with GLOST because each job has the same stresses, the scheduler, the same. The only thing is easier to submit. So the tasks, each task that it runs, it's going to stress scheduler. It's the important point. So we've got a simple example. In this example, there's an array of 10 tasks to be run, and they're all going to try to run simultaneously. We can do, if you look above that, there's ways to only run a set of them, a range. So the value that, I got to better explain this better. When your array job runs, it sets this value. The only thing different with each case that gets run is this gets incremented. So for one job that runs, it's 1, the next 2, 3. And you could do this, start from, these are different range, say 0 to 7, you could go 1, 3, 5. So if you're going to run 4 jobs here, they're going to have these different values for SLURM array task ID. And you could go 1 to 7, skipping step size of 2. So 1, 3, 5, 7, it works. And the next one is let's run 100 jobs, 100 cases. Maybe you should call it cases. I don't know, they're really jobs here. It was more of a case thing when you've got the table of commands. Anyway, so we're going to run 100, but we're going to only run 10 at once. So allows no more than 10 jobs to run simultaneously. All right, so this is all, I'm just going to demo it because it's self-explanatory. All right, so you got to, here they're trying to show you a SLURM script. This is a SLURM script, and in the example here, I've got a SLURM script. And there's more, I put more parameters here. One, because I was playing around with other things, and then I thought I'd just leave them because they're kind of instructive to get that through your head that this is per task. These parameters, these are not referring to the collective arrays that you're going to run in some manner. This is, except for the array variable itself. The others are per task. Per task meaning like per instance of this thing running. So this one is going to try to run, it's going to run an array of 1 to 9, only running 3 at once. It's exactly the same as before. In fact, this is exactly the same example as before that we just did in GLOST, and we're going to see it again in the meta thing. And so I submit that to the scheduler. So instead of using GLOST, I'm now using job array. All right, so of interest here, so it's launched the array and it's running. And it's going to work its way through the different job IDs. This is just the first set that it came that's doing right now. Notice they're on different nodes. And that's what the arrays do. They're going to pick their own nodes, or we can't have that control to put them all on one node. And it's still running now. It's up to 5, 6, 4, 5, 6. There's 10 seconds each. Almost done. Oops, oh no. Resubmit it again. No, it didn't. Okay, that just messed it up. Okay, it's getting tougher to interact here with schedule. I've got an alias to kill all the. And all right, so if we look at wrote, it just did the same thing as the last time. So it's just a different way of feeding argument into your program so that it can compute based on that value of the array. I've got one where it would do the thing where it takes longer for the one process instead of the others. I think it's kind of neat. So in the array, when it's running, when it treats the first one differently. So when it identifies that it's running the first task ID, it sets it to run for 60 seconds. All the others get run at 10 seconds, and the end result is sort of the same. The one takes longer than the others, but it does all finish up. So this one, okay, so this one is interesting because here I didn't put a limit on how many run at once, so it's going to run all of them, all the arrays at once. So because there's only 9, that's not a problem, and it's going to take, each one's 10 seconds, so they're all running, all 9 are running at once. I was actually going to do this one first, because in meta, that's what we're going to do. We're going to run them all first, and then we're going to work the other way. Run them as meta jobs. So the terminology is going to change. So it's SQ saying they're all done. And it ran it on 3, 4, launched it on 3 nodes, 3 different nodes, all those. And why not? We can create directories as we did before. Of course, we don't have to use this anding stuff here because we could put these as commands, one-liner commands on each one. That was more of a carryover from the GLOST stuff, but just to prove a point that it can be done here. If I open these in Nano, I get color. Should have been doing this all along. And so here we're going to run 3 at once, 9 tasks. And we'll just verify that it created those directories. So I can pretty much do everything in the job array that I was doing in GLOST. But GLOST is going to be more efficient because it's not launching these individual jobs. This is taking it's not practical when you've got a large number. I think it gives some ideas here in the wiki page of sort of optimal numbers. I think that's what's missing here. I should have a table for that, just to lay everything out for comparison. That'll come out next time. So 789, so it's finishing up there. So I just, I write it, so if I catting the contents of the log files that was created in the subdirectories, and it just shows that they all ran in the same node. Right, so into meta, it's gonna be sort of same format, but I cannot do it justice in the time remaining. but I can break the ice here, which anybody wants to hang around for a few minutes. I think it's worthwhile because this wiki page is pretty sophisticated read compared to the other ones. There's a lot more details in here, and it's because it's far more powerful, and it can do things like restarts and load balancing. There's conceptual stuff in this wiki page that you kind of need to filter through so that you can get up to the user level. And that was recognized in the beginning. I'm not going to repeat it because this is very excellent. In fact, there's already a YouTube video on this, which cannot be beat because it's done by the creator of this meta package, who is Sharknet Person, who is hosting right now. And that's a definite thing to watch. It brings out a few different points than are here in this detailed read. So I think the two of them together, this document, the wiki page, and the YouTube video, are pretty complementary. Worthwhile to do both, as opposed to just, I wouldn't recommend just reading this wiki page. So also watch that too. So it talks about, you can look at the benefits. This has been already looked at, and I'm not going to repeat it, but there's several reasons here that are documented on the meta page why Meta is better than GLOST. So I'm not going to repeat them. I want to get straight to the point of how do I run a meta job, because that was really, that could be seen as an achievement of sorts. How easy it is. I mean, you'll be really shocked by how easy it is. It just, it's far easier actually, and you just need to see it the first time. So that's really the value of being here right now, I would say. So you go to quick start guide on this wiki page, and just, you're going to load the module. So I already did that, so it can do it again. That's no problem. And then I'm going to, you have to get sort of comfortable with the terminology here. And that's about the farm. It's the farming of, it's a HPC term. The farm consisting of many jobs. I don't know. So I'm going to create a farm directory. I've already been in this directory and created farm 1 and farm 2. For this, I'm going to create farm 0 as per the instruction. And then I'm going to go into farm 0 following quick start guide right there. And at this point, I can almost submit the case. So what's nice here is that a table.dat, which is similar to the list .dat that we had for GLOST, has been provided. So we don't even need to generate this thing. So we can run a simple example. So once again, you got a bunch of sleep commands. It's not the long fancy thing we had before, but that can be done. And so as it says through here, if you want to run these, you can run them all simultaneously with GLOST, because there's not 900, or there's not 9 million rows here, right? There's only 18. So we can do these all at once. We don't have to partition them up into these conceptual thing of meta jobs for this farm, which basically the farm is where all your output is coming to. Now I could jump into that. I know there's going to be a problem if I do this, because there's a couple of things you have to do in here. It's probably mentioned. You probably don't have to make a change to single case. So there's the job script. So I'm not going to change the single case at all. I'm going to go on the record for this. I'm not going to touch that, because that is explored lower down in the Meta Wiki page in good detail, what can be done. And with different types of problems that you might come across. But as I'm doing a pretty simple, the sleep example, I don't have any arguments being fed to sleep. I don't need to do anything sort of exotic to get those into meta in an efficient manner. I don't have to worry about it. So I'm keeping it simple and I'm keeping the single case Dutch unchanged. So, but I do need to edit this because like any SLURM script, this is your SLURM script. You need to put your account name in it or else it's going to get a whole bunch of error messages out. And wow, that's for, I guess that's the only change for the moment. So it got 10 minutes. This thing can run for 10 minutes. And then, so submit dash run -1. So that's it. So what did I do there? I loaded the module, created the farm directory, CD'd into it, put my account name, and then did submit. And I'm going right now. I'm computing all those cases simultaneously. See that? There they are, all 18. Yeah, this is a command that comes with meta. There's a whole bunch of commands that come with meta. Let me run that one again, so you see them if they haven't quit already. One is finished. Where are the commands? Probably says it up here. Full list of commands. This is what you want right here. Number 3 takes you right there. So these are the commands that I'm running right now. So it's got them all running now. It's given them each 10 minutes. So that time limit, notice it's applied to each job, that's each case. So each line in our table, another terminology here when you touch the wiki page is case, and it's mentioned in there. So it's running all the cases right now, given 10 minutes, but they take 30 or 40 seconds. So I bet they're done by now. Oops, the SQ command. Well, SQ does it too, but list.run would not show anything at this point. And there's another one which, okay, it tells you it is done. So man, that's kind of nice. And so you don't even have to touch the SLURM commands because there's all these scripts provided here. So what can I do next? Show. I'm going to go into this farm 1. So this is exactly the same farm, but I pre-configured the job script slightly differently. So I changed another value. The time limit on each of these jobs, I changed it to be 1 minute. Now, also what I'm going to do is I'm going to use another feature of Meta, which is to run multiple cases at once. So that is, where was it? It was right there. So what we just did there was simple mode. I could have renamed that farm simple. And then this is like farm meta. So N is like your meta mode. And it's the number of, as I said, meta jobs to use. So imagine in this table, it's going to run simultaneously however many N that you have. And it's going to do that in a very intelligent way, which is explained down below. So let's run 3 submit dot run. I'm going to just I'm going to go back to 10 minutes for this one. And so once you do a run, you need to clean up, and that's okay. It's easy because it tells you to do it. So now we're back to this. Uh-oh. Okay, that got it. So we're right with this. We're using the command submit.run. N is 3. So N is, you replace N with a number. That's what it wants you to do. So it's telling you submitted 18 from the table as 3 using meta mode. So it's got plenty of time. It's going to finish all these jobs, but it's only going to run 3 at once. Let's see it doing its thing. It's kind of similar to what we were doing with GLOST and job arrays, but just way better. It's going to try to do sophisticated things like estimate if there's enough run time and whether or not it runs all the jobs in the time, if it can finish the job. It's not going to bother starting a job if it thinks it can't finish it. That might matter when you've got, you know, say 500 running at once. You underestimated the time a bit. It's not a problem. It's going to, it has under the hood some algorithms to account for all that. So it does bookkeeping. And when you use the scripts the right way, it leverages the scripts are all connected with that sort of, I don't know, you want to call it AI almost, sort of just sophisticated way of interacting with the scheduler through these scripts and through Meta itself. So once you read through the wiki, you will start to understand what I'm carrying on about. So each set of 3 here is 40 seconds. That's going to be a bit long. Again, I should have submitted it with more. So I can just kill all this. That's all right. I can demonstrate this kill. Let's go back to 3, full list of commands. Kill.run. What's kill say? Will kill all running queue jobs in the farm. Yeah, because translation, I didn't do something right. So this is my out. They're gone, and it's okay. I can redo all that. I just gotta clean it. It's just gonna redo everything. So let me just jump to the thing I wanted to do in the first place, which was demonstrate not having enough time. What happens when you try to run stuff, but you underestimate the time? So it's worth looking at this table. So roughly these things are running, say, 35 on average, 30 seconds each, maybe 35. There's 18. I'm going to run 6 at once. So 6 times 30, 180. So if I put in like 60 seconds, it's going to kill them before they've had a chance to run. That'll only let 2 get done. All right, so 1 minute will not be enough, obviously, for this whole thing to finish. And so, but that's okay. And I'm going to show how to recover from that. Submit.run and 6. Okay, so if you recall the last time it generated right, so we're gonna let's just query.run. So 8 cases didn't run. None failed. So we've got 13 here. There's 18 cases. It says 8 didn't run. So we need to resubmit to finish this. And we don't have to redo those over again. The ones that successfully ran, it's kept track of those, but it knows that some didn't run correctly. So it feels 8 of them qualify for that. So we go back to a full list of commands and resubmit run. And it's just going to use 6 again. So it's got its 8 cases that didn't get run that last time. And we're dealing with very few cases, but when you're dealing with, I don't know, 800, 900 cases and like 175 didn't run, you know, this is going to be invaluable as a tool in your toolbox for computing lots of jobs to do. And start run, let's see if we're done here. We're all going. And what we're looking for at the end is that successful message from query.run. I have not got to the status.run. No. So, so those are getting done. Looks like this is a way to check how things are moving without going through the scheduler. Oh, still got one. We're almost there. Query.run. 0 failed. 1 didn't run. Oh, so, but not a problem. I just want to be sure nothing's sitting around. I trust it. Honest. This is the first time using it, so trust will build more as time goes on. So I'm just going to have to do it again to clean up that one, and let's see if it'll get it. This may be, and it may have been mentioned somewhere in here that that's a bit of an iterative process. This resubmit is all discussed down in here. So we've got one job. It's got one job, and it's running it. It's that sleep. One of those sleep commands didn't work for some reason. That's okay. That's what happens when you underestimate the time. You need to go back. Now, what I'm not quite, I would really like to do one more. If you can just give me one more minute. All right, so the query. Yep. So there's another way to go here, and there's another option. So when I submit, use the auto switch. Oh, I gotta clean up. So when you use the auto switch, it will automatically do those resubmissions. So I'm gonna have to call it right here. And there's more stuff to do, but maybe I'll end up doing this again anyways, because we didn't push out the email again this morning. So I think a lot of people didn't show up. It doesn't hurt to do this again. So yeah, I had another farm, bunch of examples, but it's going to take another half an hour. So